Hi everyone, my name is Piyush. Together with my co-author Lampros at LoopMe, we developed this piece of work titled Hybrid Dual Censored Joint Learning of Reserve Prices and Bids for Upstream Auctioneers. Outline is as follows. I will start with a brief introduction to the problem and will highlight the closest work in this area. Next, I will formulate the problem in detail. Finally, I will describe the proposed method with the experiments. It is logical to explain the flow of an add request in our setting. Basically, each add request originates from an SSP, so-called downstream marketplaces, under a specific auction type, first or the second price. Each SSP forwards the add request to its bidders, each of which might be a DSP or other marketplace called the Upstream exchange. If one of the bidders is capable of reselling the same opportunity, that is an exchange, the reselling auction is referred to as an upstream auction. Lastly, the exchange submits a bid to compete downstream. If we focus on the profit maximization problem for the exchange, this is achieved by jointly learning the upstream reserve price and downstream bids. There are certain challenges associated with the problem. For example, the optimization needs to be performed jointly due to the profit being contingent on winning downstream. Secondly, there is censorship on both upstream and downstream markets. Lastly, there is no significant research in current literature that describes how to exploit the coexistence of both options. Hence, we also study these options that we refer to as hybrid. There are practically two closely related works in setting with intermediaries. Lisbona et al. Presented the reserve price optimization in the presence of second price upstream options, while Zhao et al. Presented on the bid optimization in the first price strategies. However, there is no work that focuses on the joint optimization of the two. This is where our research plugs in. With that, let's jump into the problem in detail. The add request originating from the publisher arrives at the SSP, which then passes it to its bidders. One of them is our modeled exchange. We assume that the upstream auction is same as that of the SSP. The clearing price of the upstream constitutes the revenue, and the clearing price of the downstream is the incurred cost for the exchange. The profit is maximized by extending the original reserve price of the SSP by a linear multiplier alpha, and then bidding downstream by decreasing the revenue of the upstream auction by a bid shedding factor beta. Alpha is greater than equal to 1 and the bid shedding factor beta is between 0 and 1, because the exchange cannot bid more than its valuation and exchange cannot bid less than the SSP reserve price. We develop our strategy inspired by the exploration-exploitation trade-off. There are two kinds of censoring in these markets. Upstream DSP's bids are left censored, meaning that they are only observed above the set reserve price. And the downstream winning feedback is right censor in the second price and left plus right censor in the first price, meaning that the true unobserved winning price is below and above the bidder's bid price, respectively. To deal with censoring, we implement a dual exploration independently for alpha and for beta to learn the censoring patterns in 4 dimensions. Although the reserve price is only left censored, to capture the DSP's bidding behavior for alpha, we also perform right exploration along with left. With the collected exploration data DE, we pick alpha and beta such that maximize the profit function. We utilize binning to group the continuous values into a smaller number of bins, NB alpha and NB beta. The means of the alpha and the beta from the bucket that maximize the profit are chosen for the exploitation. Note that since the bidders are assumed to truthfully bid their valuation in the second price, there is no exploration performed for beta. So we only need to learn alpha. In a hybrid setup where the same inventory is sold using both auction types, we propose an elegant inferential strategy inspired by the Revenue Equivalence Theorem. In this approach, we make use of the estimated winning price W2 from the second price traffic of the same inventory and utilize it in the first price traffic by adjusting the original mean and max of the betas as shown in the formulas. In this way, we are narrowing down the range of the exploration, and hence we are avoid unnecessarily exploring in non-interesting areas, which reduces the exploration cost. We use the data from the last 3 weeks at the LoopMe exchange that comprises the 50 different placements. 10% traffic correspond to the baseline group, the 10% to exploration, 80% to exploitation. The exploitation group optimize the optimal value that were obtained from learning using the exploration. The test group combines exploration and exploitation. The evaluation metric is the profit lift between the two groups. Proposed method is compared against a baseline strategy with manually set multipliers. For this strategy, in the first price auction, the SSP reserve price and revenue at Upstream are increased and decreased respectively by the same 1.25. In second price, beta is set to 1, that is a truthful bidding. We use the fine-tuned parameters of the exploration bounds for the alpha and beta and the minimum traffic per bucket. A different experimental design is required for evaluating the hybrid placements that use the two strategy with and without revenue equivalence theorem. To compare the two on the same set of first price placements, we alternate every 4 days between the two approaches, but use only the most recent 48 hours to measure lift. This discards the exploration data that had been exposed to the previous strategy. Table 1 displays the results for the non-hybrid placements. Alpha star bar and beta star bar are the averages of all the overlay values of the alpha star and beta star which were used in the exploitation group. Let us look at the first scenario. Clearly, the higher the reserve price, the lower the probability that the upstream auction will clear. Hence, we observe the lower success rate in the test group. However, the higher the reserve price, the forces the bidders to bid above it, which when passed through a higher bid due to higher beta, increases the number of wins per success. The opposite happens in the second scenarios. In the third and the fourth scenario, it is not only the relative differences, but also the actual values of alpha and beta that dictate the ranking of the wins to success rate for the two groups. For example, the impact of the higher reserve might be dominated by the lower bid and vice versa. In second price, there is only alpha, hence the explanation is more straightforward. In general, there exists an inherent trade-off between the win rate, and that is win divided by the request, and profit per win. The variation in the profit lifts also depends on the heterogeneous nature of the placements and other attributes. For the first price traffic of the hybrid placements, we compare DCGL method against the DCGL RET method. The results so cautious that the inference setup has significantly increased the profit lift. General summary is as follows. The lift is slightly higher in second price because here optimization requires learning only alpha. Hence, the exploration cost is lower, whereas the joint learning of alpha and beta in first price increases the exploration cost. The heterogeneous nature of placement may also justify the differences. For the hybrid placement, inferential learning using RET has played a significant role in increasing the profit. We quantify how exactly the exploration cost was reduced by using a custom lift metric, exploration profit lift, which is measured only using the exploration sets of the two methods. To conclude, in this presentation, we introduce an efficient framework for jointly learning upstream reserve price and downstream bids for the first and second price options in a dual censoring environment. We propose an elegant strategy based on the Revenue Equivalence Theorem to deal with the hybrid event. A/B tests performed at the LoopMe exchange validates the effectiveness of the proposed method in practice. Future work could include, for example, learning the nonlinear functions of the bids and the reserve prices. Thank you, and please reach out with questions or feedback.